Okay, so you would have already seen how to handle nonlinear systems which do not have an input. Now, a very clever thing which was done was that when you try to analyze these nonlinear systems which do not have an input, you can actually decompose that into two separate things, one a linear system and the other you pack all the nonlinearities together. And then when you want to talk about the stability of the equilibrium point of this nonlinear, the original nonlinear system, that is equivalent to talking about the stability of this interconnection between the linear system and that nonlinearity. So, let me try and explain what I mean by this. Okay, so suppose you were to look at an equation like, let us say, the second derivative of y plus let us say the first derivative of y squared plus let us say 2 times y equal to 0. Now, one wants to analyze this system. This system is a system without any inputs, and there are well known methods of trying to analyze this system, but what I was just talking about was this clever way of thinking about this system as an interconnection between a linear system and a nonlinearity. Okay. So, now let me try and give you how that is done. So, think of this equation d2y dt squared plus 2y equal to u. This now is a linear system. Okay. Now, this is exactly like this equation, except that you could think of this dy dt squared as minus u. So, let me put that as the next equation, which is u equal to minus dy dt squared, and this is the nonlinearity. Okay. Now, the interconnection of these two systems then would give us exactly the same as this original nonlinear system. Okay. So, let us look at what this interconnection would look like. So, if you look at that system d2y dt squared plus 2y equal to u, this is a linear system which has transfer function given by y(s) by u(s). This is the transfer function g(s), which is equal to 1 upon s squared plus 2. Okay. So, now let us think of this g(s) in this way, and here is the input that you give, which is u, and the output that you get for this, which is y. You take this y and put it to a nonlinearity, and this nonlinearity has the characteristics that if the input to the nonlinearity is psi, the output is psi squared. Okay. Now, in this case, if we now feed back this thing with a negative feedback, then if this E, which is the input of this feedback loop, if this E is set to 0, then what we would be looking at is exactly the original equation that we had, which is d2y dt squared plus dy dt, the whole thing squared, plus 2y equal to 0. So, talking about this closed loop system being asymptotically stable, for example, is exactly the same as saying that the original nonlinear system is asymptotically stable. Now, of course, in this system we can clearly make out that the system would have the, I mean, if you draw a phase plane portrait of the system, then the origin is an equilibrium point. Now, the origin is an equilibrium point if one wants to find out whether this origin is, let us say, asymptotically stable. That is the same as in this feedback system, whether that given system, this feedback system, is asymptotically stable. So, if you set up this feedback system and set y with some value, and then you let this system evolve, and if this system evolves finally settling down to the value y equal to 0, u equal to 0, then what that would mean is this system is asymptotically stable, and what that effectively means is that the original nonlinear system is effectively stable. Now, this clever trick is, I mean, once this clever trick was discovered, this was used again and again. So, the nonlinear systems were analyzed by looking at splitting it up into a linear system and a nonlinear part, and looking at the feedback connection of this linear system and this nonlinear part. Now, once that was done, then people came up with some sort of a conjecture. Now, so let me give you what this conjecture was all about. Okay, so suppose you had a system like, let us say, similar to the earlier one, but d2y dt squared plus, let us say, 3 times dy dt plus, let us say, 2 times y plus y cubed equal to 0. Okay. So, this now can be split up into a linear system. So, the linear part would be given by a transfer function which is 1 upon s squared plus 3s plus 2. And the nonlinearity that you would interconnect with this linear system is given by something where if psi is the input, the output is psi cubed. Okay. Now, if one looks at this nonlinearity carefully, this nonlinearity, so suppose I think of psi, which is the input to the nonlinearity, then the output to the nonlinearity is here, and this looks like something like that. Okay, so that's psi cubed. Okay. Now, the conjecture which was made by a person called Eisenman, and Eisenman made the following conjecture, that suppose you have a nonlinearity, and let us assume that this nonlinearity is memoryless. Okay, so what do I mean by memoryless? What I mean by memoryless is that this nonlinearity, it only the output of the nonlinearity only depends upon the instantaneous input. Now, the earlier nonlinearity that we looked at, where the input was psi, the output was psi cubed, and this output was independent of what the past values of inputs were. Yeah. So, it is a sort of the output only depended upon the instantaneous input, and so one could think of this nonlinearity as a memoryless nonlinearity. Okay. So, typically if you look at a nonlinearity which is memoryless, it might be, something like that. Okay. So, this here is the input to the nonlinearity and this is the output to the nonlinearity. So, when you have this as the input, then the output is this value here. Okay. And since it just depends on the okay, so this curve of course is a slightly twisted curve. So, it looks like with this input there might be multiple values, but let us assume that the curve was straight enough so that such a situation never arose. Okay. So, the output purely depends upon the instantaneous value of input. Now, the conjecture was made by this person Eisenman, and his conjecture was the following. You see, if you look at this nonlinearity, at each point there is some tangent to the curve. Okay. Now, one way that you could talk about this nonlinearity is you could limit the nonlinearity. So, this particular nonlinearity, for example, one could say that 0 is less than equal to f of xi by xi, which is less than equal to infinity. So, this is a nonlinearity whose slope, instantaneous slopes, lie between 0 and infinity. Okay. So, of course, I am sorry, but initial curve probably had slopes which were greater than infinity, but this one is some trajectory or this is a nonlinearity which has its slopes lying between 0 and infinity. Okay. Now, if one looks at such nonlinearities, so let me give some more examples of similar nonlinearity. So, you could have a nonlinearity like that, and then clearly all the slopes of this nonlinearity lie between this line. So, if I call the input xi, so this line is k times xi or k1 times xi, and there is another slope here. So, this is k2 times xi, and so this particular nonlinearity, one could say, satisfies the characteristics that f xi by xi is greater than this particular slope k1 and is less than this other slope k2. Okay. Now, suppose we interconnect this nonlinearity. So, this nonlinearity is interconnected with a linear plant Gs, okay, in this feedback structure, and then suppose this linear plant was such that if instead of the nonlinearity, you used a linear gain k, and this k was between k1 and k2, and the resulting linear system was stable, then Eisenman's conjecture was that if you put the nonlinearity instead of that linear gain, then the resulting system would also be stable, would be asymptotically stable. Okay. So, the idea being that if you are at this point and this was the input, then there is some slope here, correct. Now, this slope, when you put that linearity, the resulting system is stable or asymptotically stable. Okay. Now, if the resulting system is stable, then the guess was that for the nonlinearity, because locally it is like this linearity here, therefore, it will behave nicely. So, now as a result, of course, the system evolves and you go to some other xi, and at that xi there is some other slope. Now, this slope, when you put in as the linear thing, then again you get a asymptotically stable system, asymptotically stable linear system. Now, working in this way, the guess was that if you had a nonlinearity which lay in some sector, so this particular nonlinearity f of xi is said to lie in the sector. So, it is a nonlinearity which lies in the sector k1, k2. Okay. So, if you have a nonlinearity which lies in the sector k1, k2, then if the linear plant is such that when you put feedback gain, any gain between k1 and k2, and the resulting system is asymptotically stable, then if instead of that linear feedback you put the nonlinearity in there, then the resulting system is going to be asymptotically stable. So this was Eisenmann's conjecture. Okay, so perhaps I should just sort of formally write it down. Okay, so suppose that the linear feedback system is asymptotically stable for values of k in the range k1 to k2, then a nonlinearity that belongs to this sector, which is equivalent to saying that the nonlinearity f xi by xi, this is less than, I mean k1 is less than equal to this, and which is less than equal to k2. Okay. Then a nonlinearity of this kind in feedback with the linear system is asymptotically stable. Asymptotically stable. Okay. Now, this is Eisenmann's conjecture, and this was given roughly in 1949. Now, initially it was not clear whether this way of looking at nonlinearities as approximation of linear systems is going to work. And in fact, in the literature for some time this used to be called the method of linearization, because the idea was that you have this nonlinearity, and at instantaneous at various instants for a given input there is an output, and there is also the slope of the output according to the characteristics of the nonlinearity. And then Eisenmann's conjecture essentially said that if for all those slopes that you get in the nonlinear function, I mean if for all of those, if the nonlinearity is in that particular sector, and for those gains it turns out that the given closed loop system is stable, then the closed loop system is stable if you put in the nonlinearity. Okay. It turns out that Eisenmann's conjecture is false, and this was proved by several people over the years. Several people proved this thing. So some of the more famous names include Hahn, who did this in 1963, then Willems. So Willems showed a counter example that this doesn't hold. Willems did this in 1966. Then there was Fitz, who did this also in 1966. So they constructed all sorts of examples which showed that this conjecture of Eisenmann is not correct. Okay. Okay. So let me now give an example of a system where this actually doesn't hold.